If we start with a bare, empty nucleus in a vacuum, we can see exactly what happens when fast-moving particles, electrons, are introduced into the space. Immediately, these electrons face a physical dilemma. They are intensely attracted to the positive charge of the nucleus, but as negatively charged particles, they violently repel each other. To exist in a stable arrangement, what physicists call a ground state, the atom has to balance these competing forces by solving a precise spatial puzzle. The first rule of this puzzle is the Aufbau principle, which translates from German to building up. Electrons are inherently lazy. They will always seek the lowest available energy level first. The first electron drops into the absolute lowest energy tier available, settling into the 1s position. When the second electron arrives, it seeks that same deep valley of stability, dropping directly into that exact same lowest tier. The Aufbau principle acts as the atom's vertical architect. It guarantees that the structural foundation is solidly packed before any electrons begin building higher. But this creates a structural bottleneck. If every electron wants the lowest possible energy, why don't all of them simply cram into that bottom 1s level? The answer is the Pauli exclusion principle. This rule dictates that no two electrons in an atom can ever share the exact same set of quantum numbers, or quantum state. This diagram shows the only way two electrons can share the same orbital room. They must have physically opposite spins, represented here by one arrow pointing up and the other pointing down. Once those two opposing spins are locked in, that specific orbital is entirely full. Any subsequent electrons arriving at the atom are forced to move up into higher, less ideal energy levels. This brings us up to the 2p subshell, featuring 3 separate orbital rooms at the exact same energy level. The first electron drops in without issue, but the following electron faces a choice: pair up in the occupied room or take an empty one. The answer was discovered through the observation of atomic spectra, leading to a guideline named after physicist Friedrich Hund. Hund's rule states that electrons will always completely occupy equal energy orbitals singly, and with parallel spins, before they ever begin to pair up. These box diagrams of carbon and nitrogen show us the physical reason for this behavior: Coulombic repulsion. Forcing negative charges to share a tight space requires extra energy, so the electrons spread out across the empty boxes to maintain a low energy state. If we look at these incorrect arrangements marked with red X's, we see the consequences. Pairing them too early or flipping their spins in empty orbitals creates an unstable, high-energy arrangement that completely violates the atom's goal. If the Aufbau principle dictates the vertical floor plan of the atom, Hund's rule dictates the horizontal seating arrangement, keeping the electrons as far apart from each other as possible within their allowed tier. Looking at the completed structure of an atom, we can see how these rules operate simultaneously. They pack the inner core tightly while meticulously spreading out the outer edges. These rules are physical manifestations of a universal directive. Matter will always find the path of least resistance and lowest energy. Because electrons sort themselves this way to minimize their energy, certain atoms are naturally left with unpaired electrons hanging on their outermost edges, desperately searching for a connection to achieve stability. This exact quantum algorithm determines how atoms bond and react with one another. These tiny optimizations are the core engine driving all chemistry, biology, and matter in the universe.